there's a little bit of a different title in my talk too, I'm afraid. As it was said, I'm Nicola Guerrini. I'm the group leader at the CMOS Sensor Design Group at STFC in the technology department. And we've been developing CMOS sensors for electron microscopy for the past roughly 15 years. A brief outline of my talk, give you a quick introduction, just to set the scene, give you also a brief outline of the development of the different detectors for transmission electron microscopy. And then the two main topics that I would like to address today are the developments that we made at STFC in terms of CMOS sensors and what we see the future should be. And for what concerns the future outlook, just would like to say that it's a very IC designer perspective, what I can give you here. So I also would welcome the opportunity to hear from the users, from the scientific community, what really would make your life easier or the science that we can collect better. And I'll finally conclude the talk just with a quick summary. So the starting point is detectors for electron microscopy. So the electron beams that we've seen in the previous presentations will hit the specimen, then will generate not a projection, will generate something else. Then is converted into an image, an image in an electronic format that can be processed, as we've seen also this morning. So historically, film have been used for a long time. They have a fairly good resolution. They have the disadvantage of being a non-digital means, so you have to develop it after, obviously being a film. And the signal-to-noise ratio was not brilliant, especially for very weak beams. They were replaced starting from the early 90s, if I'm not mistaken, with CCD coupled with phosphor. They had the advantage of being very good, for example, for tomography, to be digital recording, so your image was out very quickly. But the phosphor will somehow affect the quality of your image, and is also non-direct detection because you're going through this phosphor. CMOS sensors allow to have the best of both worlds, effectively. So it's digital, it's a direct detection, a good spatial resolution, and it's also resistant to the radiation, so that it doesn't get damaged like a CCD camera would do. So as I said, this is effectively a development, just to give you an idea of development that have been going on. So there's different sensors from FEI, for direct electron, from Gatan. I'm sure I left a lot of these other developments out of the list. The main concept that I would like to transmit is the fact that, you see, development was quite slow, and then sort of ramp it up to the point that almost every year, if not every few months, there's a new development, a new sensors, faster, larger, with different features. So also from the detectors point of view, this is a field that is really growing. Let's start from the basics. So how do we detect electrons in a CMOS sensor? You can see electrons go straight into the silicon. The silicon can be divided effectively in three areas. That's where the electronics, the transistors are. This is the epitaxial layer, lightly doped. That is effectively the sensitive volume. And then there is a substrate. We'll see that sometimes we do without the substrate also for better performance. Charge is generated and then collected with a normal diode. So what are the advantages? Advantages are direct detection, as I said before, no loss of resolution. Radiation hardness, well, electrons do damage the specimen, but will damage also the sensor. CMOS can be designed and fabricated in a way that is tolerant to radiation, so it doesn't get damaged, it doesn't lose performance. Images can be recorded in a digital format, as I said before, and because it's CMOS, it's the technology that is used in the electronics of everyday life. It's a technology that is in PC, in mobile phones, so it gets a lot of investment in terms of development. So if there are new features, new opportunities, we will be able to tap into this because that will be done by big players, big companies. There are examples of what I'm saying later. Well, as I said, a long time ago, roughly 15 years now, and we use one of our CMOS sensors. This, as you can see, is a very rough setup, and we tested in an electron microscope at LMD, and this is the actual first image that we got. So we proved that okay, this can work, and this can work pretty well. And obviously, you cannot jump straight away into developing a new product, so you have to test a lot of different features. So we started a project that we call PEMAPS. This TEM is pretty obvious. APS stands for Active Pixel Sensor. In theory, it should be Active Pixel Sensor for TEM, but it didn't sound very good, so PEMAPS stayed. We started with smaller test structures. You can see this is an 8-inch wafer. Each one of them had 25 different pixel topologies with a fast analog readout. Analog because it's simpler and can be made resistant to radiation easily. And the region of interest addressing. Try to put a lot of features also that normal cameras have. This is a 1.5 million pixel test structure, and we started to collect fairly decent images with this kind of sensors. The reason for the large number of pixels is that radiation damage, radiation hardening, it's something that is quite hard to simulate. At the end of the day, you have to try it in a microscope and you have to see what's working, what's not working. And it's also very technology dependent. If you're using a supplier of CMOS process A and a supplier B, you will find that you do exactly the same things with very different outcomes. And here's the reason. So radiation on a very large, on CMOS sensors, this is actually a picture of the 16 million pixel sensor, can lead to a buildup of charge in the oxide. This, I'm afraid, is a very naive cross-section, but it sort of gives you an idea. This is the substrate, this is the oxide, this is a polysilicon. And this positive charge here can affect your electric field, it can affect your transistor performance. If you imagine here, if there is a buildup of charge, you might end up short-circuiting the two terminals of the transistor. So what do? You do it without. You change the layout of a transistor. So instead of being just a linear transistor, is what is called an enclosed layout transistor. So you don't have these edges anymore. So whatever damage happens in this thick oxide, there is no thick oxide here. So your transistor is resistant to radiation, up to a certain point, of course, but it will give you very, very good performance. There are also other tricks that you do in the design, but this is just to give you an idea what the designers have come up in order to make sure that we can put a sensor directly in the electronic beam. The second part is the size. The second point I want to address is the size of the sensor. Now, sensors are fabricated using masks. This mask is normally addressed to as a reticle, and the size of this is, depending on the foundry, but it's between 2 and 3 centimeters in both directions. That is, in theory, the maximum size of a sensor that you can build in one single exposure, in one single processing step. Because we wanted a much larger sensor, and we had to find a way to do it differently. But these kind of developments in the CMOS world are extremely expensive. But luckily, as I said before, we could tap into developments that were already happening. And we use a technique called stitching. So your reticle is not the full sensor, but is effectively a collection of different blocks that you can stitch together. So what you stitch together is during the wafer fabrication, you step and repeat part of these masks, like the animation is trying to suggest. So what you see, this area here, that could be, for example, in this specific case, it is, let's say, 1K by 1K pixel. You repeat it in a 4x4 array, and you have your 16 million pixel sensor. You can, in theory, extend it for the entire area of the wafer that you have available, but that will be a very large sensor. The result is this. This is a picture of the wafer that is with the sensors for the Falcon 2. And you can see that on our 8-inch wafers, there are only 4 sensors. Each one of these sensors is effectively 6 by 6 centimeter. And we can have a look at the different areas. Pixel array is obviously the biggest part of the area. There's also electronics to control the readout mode on the road. So these sensors are read out in what is called a rolling shutter way. So you read one row at a time or a number of rows at the same time. There's readout electronics and column controls, and then the auxiliary electronics is normally in the corners. As you can see, it's a very large sensor. And this is the final product. The final product is the CMOS sensor for electron microscopy. As far as you know, it was the first CMOS sensor stitched. It is currently using in the FEI Falcon line for direct detection. You have a summary of the performances here. So 16 million pixel analog outputs, fairly decent frame rate, and with this might not be very important from the scientific point of view, but it's 0.35 micron standard CMOS process. You can see it's a relatively old process. It's not actually state-of-the-art. You have now things, 10 nanometer, 12 nanometer, this kind of things. So this is very old, but makes it for a very, as you say, commercially viable product. And with the result, if you can achieve certain kind of results with this cheaper technology, is always better. As we know, CMOS sensors have been instrumental in effectively changing the landscape in electron microscopy, and they started what has been defined by Werner Kulbrand as a sort of resolution revolution. And this is actually an expression that probably has been abused several times. So, to the point that the author, I know, is actually sick of it now, but let's move on. I'm an integrated circuit designer, so sometimes the medical subtleties of structures are not exactly my forte, but this is a slide that I always use to explain why electron microscopy going from 12 angstrom resolution to 2.2 angstrom resolution is important. You don't need to be an expert in the field to understand that this side of the image looks definitely much better and with much more information than the other one. So this is really a visual impact of what CMOS sensors are helping achieving in electron microscopy. If we want to measure this kind of improvement in performance, so yes, things have changed, but how do we measure what we are achieving here? And the most important requirement is a high detective quantum efficiency, referred to as DQE. The reason is we use this parameter is because it incorporates detection efficiency, spatial resolution, and noise properties of the detector. And DQE is defined as the ratio of the signal to noise at the input of your detector and the signal to noise at the output of your detector. Because no detector will be noiseless, I mean, DQE will always be less than 1. We try to make it as close as possible to 1, but it will be always less than 1. And you can see a plot here of different sensors, of the DQE of different commercially available sensors as a function of the spatial frequency. You can see that compared to film, direct electron, FEI, and GATAN, they're all well above. So CMOS clearly gives you an improvement in performance. We can argue about the low spatial frequency, high spatial frequency advantage, but this is where the field is going with the help of CMOS sensors. We have to consider also something that I think was mentioned in a previous presentation, that is electron counting. I mean, all these images, the DQE that I've shown you before, it's obtained in integrating mode, so as a sort of standard imaging mode. When we switch to counting mode, so we are physically counting the different electrons, you can see that the performance in terms of DQE really shoots up. And you can see this, for example, is the Falcon 3 from FEI in 3 different configurations in counting mode. Electron counting requires a very high readout speed in terms of frames per second. This is very important because if you compare these two plots, for example, Falcon 3 versus K2, you see a very big difference in DQE, but you have also to take into consideration how many electrons per pixel per second were used in this experiment. You can see that the K2 is roughly a factor of 10 compared to Falcon in terms of flux, and this is due to the fact that the K2 is a faster sensor in terms of frame per second. What else can we do to improve performance? Well, what we can do to improve the DQE is, for example, thinning the detector. I mean, you can see 300 kV electrons goes into silicon. There's a lot of scattering happening to a volume to 350 micron, probably in the Z direction, maybe even more. If you can thin down your sensor down to 35 micron, you can see that the amount of scattering is definitely less. So back thinning, removing a large part of the silicon substrate that I'll show you, I think, on the second or the third slides, dramatically reduce the back scattering. And this is also proved by the fact that the DQE between the FEI Falcon 2 and the FEI Falcon 3, that is much more heavily back thin, you can see the difference in performance. You can see the difference in DQE. And the improvement are also for more, let's say, optical performance, like the MTF. The MTF will give you an idea of the sharpness of your image from a certain point of view, and is heavily affected also by the thickness of the sensitive layer, of the epitaxial layer with the charge generated. We have collected data in two different scenarios with the thin and thick epilayer, showing that in both cases, decreasing the sensor thickness will make your MTF better. So back thinning effectively helps you in terms of DQE and an MTF. Just one last slide on the single electron detection. So when you have events can be very neat events, so the electrons go through and nothing else happens, or you can have events when there is a scattering. If you can count your electrons, the performance will be much better. Your images will be much better. The science that you can do will be much better. This is an example of what I said. Good event, the electron passing only in one direction and not any back scattering. And bad event is when the electrons start to straddle around and generate charges of many different pixels. You can imagine that trying to isolate this as a single event, is actually quite challenging. This is so what I talked about so far is effectively the development that we've done at STFC. You can imagine there are other developments ongoing at the moment, going more or less in the same direction. But what I would like to share with you is some kind of outlook. How do we achieve the full potential of electron microscopy from a detector point of view? And I've used as a starting point the outcome of this recent publication, where two limiting factors were identified. I mean, the first one was electron beam sample movements, very well explained in the talk right before me, and the efficiency of the detectors used to record images. And I made also a note about the fact that in this report, some kind of entry-level cryo-EM has been suggested as a way to expand the possible pool of users and helping in preparing the sample and having an initial evaluation. There is something that was mentioned by Chris in his previous talk, I think on one of the last slides. So what can we do from the detector point of view? Detector performance, well, fairly easy. Low noise, because of the way DQE is defined, low noise will give you better signal-to-noise ratio, hence better DQE. It will help you also in doing single electron counting, but where the frame rate is also essential, and back thinning we see playing a very important role. From the sample movements point of view, obviously the detector there's very little that can do, so I'm not going to enter that kind of argument. The only thing that I can say is that fast readout would probably also helpful in assessing what is happening, especially at the beginning, for example, of irradiation to the sample. We can probably track the sample a little bit better. Bottom line, readout speed is a crucial parameter in this case. Not very easy. If we go back to the detector that I've shown you before, this is a 6 by 6 centimeter. There are pixels scattered everywhere, and all these pixels will have to be read out with some electronics that is in the bottom area. That means that all these pixels are connected to very long vertical columns that have a certain resistance and a certain capacitance. And there's very little that you can do about that. And a signal that will go through such a RC network will be somehow delayed, and it will take time to settle. This is physics. There's very little that we can do. But how can we go fast in terms of frame rate? By reducing this distance, so by avoiding that the pixel information has to travel so long before being processed. Well, for the moment, we can see two possible ways of doing it. First of all is move the electronics back into the pixel array, or use a 3D stacked approach. For the in-pixel electronics, instead of having a very simple pixel where you just detect the charge and send the information out to the electronics, we can think of a very complicated pixel. A complicated pixel where, for example, there's analog to digital converter, there's signal shaping, processing, memories, you name it. I mean, these are things that can be done, they happen, I mean, for other applications. For example, at STFC, we developed a sensor for time-of-flight electron microscopy with roughly 700 pixels, 700 transistors in one individual pixels. With a little bit of imagination, you can probably recognize here the 4 diodes and some metal tracks running in all directions. The second approach, in order to have the information out of the pixel array very quickly, is to have 2 CMOS sensors, one on top of the other. This is a so-called 3D approach. That means that the information from the pixel array gets transferred immediately to a second layer where the analog to digital conversion is effected straight away. Immediately in the digital domain, you can go much faster and achieve a performance of several thousand frames per second, even for larger detectors. What is the problem in this case? The big problem in this case, radiation hardness becomes very demanding. The electronics that was previously outside of the pixel array, so could be protected from the electron beam, is actually in the electron beam now. So it will be damaged by the electrons. So all of these electronics has to be designed in a way that is tolerant to radiation. We cannot forget other factors like technology scale down, so we could even put more complex electronics. Larger sensor going beyond the 4K by 4K, fully digital sensor, taking full advantage of the functionalities that CMOS can allow, and data storage, data compression, for example, very large sensors, several thousand frames per second, 16-bit resolution, that will generate a terabyte and terabyte of data very, very quickly. And we've seen this morning how much processing happens on these images. So this will make things very, very challenging. Last but not least, power consumption. These detectors are in vacuum. They will have to be cooled in vacuum. So if you have a lot of watts on your sensor, it will be a very challenging task. I put some notes here for what concern indirect detection, because some of these CMOS sensors can be used also with a scintillator, like the way the CCDs. I mean, in the presentation this morning, the CETA sensor from FEI was mentioned. That is exactly what is all about. And you can see that we're sort of going more or less in the same direction. So the increased frame rate seems to be some kind of recurring theme. And close my talk by maybe just a quick summary. The fact that CMOS technology has been a disruptive technology for concern the electron microscopy world. Detector development that we've done at STFC are now using commercial products from FEI, something that obviously we are extremely pleased and proud about it. There are other competitors also in the field proving the fact that this is the direction to go, and there's a lot of results that now have been taken with camera that we developed at STFC. Just would like to thank people who have contributed with images and comments to this presentation, and my group at STFC. And last but not least, I would like also to thank you for your attention.
Thanks, Nicola. Thanks. Questions? So, I have one. I don't know if
it's a good sign or a bad sign.
I was just wondering, has the back thinning reached its limit, or you expect these to go even thinner? Is it possible, and will it help?
The back thinning has not reached its limits, because at the moment we are working with the substrates that are in the region of 20 to down to 6-7 micron. So if you include also all the metal stack, going below 30 micron in total thickness can be quite challenging. But if you use more aggressive technology with thinner epitaxial layers, you can probably thin it down even more. At that point, you will have two problems. The first one is you have to handle a 7 by 7 centimeter piece of silicon that is 20 micron thin, not very easy. And the second one is getting the right ratio between the epitaxial layer thickness and the pixel pitch, because that is key to the performance.
I have a question about, you talked about all the things that can be done to improve the performance of the CMOS detectors. If you got everything you wanted, what do you see, what projections do you expect in terms of increased data storage that are required?
Well, you can see at the moment, I think the faster CMOS sensor in terms of frame rate is a Gatan K3 at 1,500 frames per second. And you can see that, well, if you want to go beyond that, you will start to have, I don't know, 2,000–3,000 frames per second on a sensor that has at least 16 million pixels. So you can see it's a gigapixel, it's several hundred gigapixels per second. Each pixel can correspond to roughly, I don't know, 12, 14, 16 bits, depends on your resolution. So you can easily go into the terabyte. I mean, if you go in at 3,000 frames per second, you will fill a terabyte disk very, very quickly. So it can be extremely, extremely challenging from that point of view. And judging from what I've seen this morning, producing and storing those data would be only half of the problem. The other half of the problem, or maybe the other 90% of the problem, is actually processing and handling all this data. That's why in my slide I put a mention of the data, because at a certain point we will reach the point where we can acquire very, very good data, very good images, but do we have enough capability to process them? So the two things will have to go in parallel, I would say.
I was just curious about the mechanism of failure in these when they're not so radiation hard. What kills these pixels? Is it the readout electronics that fail, or is it actually damage to the pixels themselves? Or?
Well, the sensor that we have designed so far, they had rather hard electronics everywhere, also in the shielded area, so we don't know exactly what is their tolerance. At the moment, the sensor works in the region of 20 megarad. Obviously, the pixels are the most delicate part. Main mechanism of failure are the leakage current from the diode becomes too high and kills completely your dynamic range. We've seen in a couple of examples that electronics are very close to the edge of the pixel array, so not very well shielded. After very heavy doses, tend to give you problems, because it's a digital block, it gives you problem like single event upset, these kind of things. So these are the two main failures, but the pixel array, I would say, is 99% of the failures that we've seen so far.
Okay, you showed us a picture where there was double deposition per electron in an image. So I want to know, how have you solved that problem? Do you do it by post-processing, or has back-thinning or something reduced that?
You mean the bad event, good event,
yeah, exactly.
bad event, good event picture. To be honest, I don't know the details of how that kind of processing is done. My understanding is that the point of entrance of the electrons is normally where you have the lowest signal, because the scattered electrons tend to deposit more energy, so you can sort of retrace it back in this way to the point of entrance, because what you want at the end of the day is the position of the electrons. You want to counter the electrons and the position of the electron. But apologies if I said something that is...
I mean, does your detector give us that raw image, or do you do some processing to it before you
this is another bone of contention, because in order to reduce the data rate, I would say that we suggested several times, can we do some processing on the ASIC, because that will reduce the amount of data that has to be handled. But the scientists are very reluctant to see any processed data, even if you correct for some dead columns, they want to see the dead columns. So it becomes a little bit of a challenge for us. From a certain point of view, for us it's simpler. We just provided the raw image. So But yeah,
Yeah.
that is part of the conversation that I was mentioning before.
Okay, thanks.